Hi there. So today we're going to continue our talk about optimization. The other day we talked about optimizing distance problems, which typically mean you're looking to minimize distance. You want always the shortest route to get somewhere. Today we're going to talk about minimizing time or optimizing a time situation. So we probably want to get somewhere as fast as possible, which means the least amount of time to get somewhere. So we do need a formula for time. Formula for time is linked to the formula for distance. So formula for distance is velocity times time. So isolating the t gives us our formula for time. So the question we're going to look at today, it's a classic, it's got lots of applications, and it typically starts with, I need to get from here to here in the shortest time possible. Or it could have been from here to here, so direction doesn't matter. So what is the shortest, not time, what is the shortest distance? Going straight there. Without a doubt, the idea of Pythagorean theorem, that's my shortest route, versus all the way here and then all the way here. That's going to be the shortest versus the sum of these two. But these questions will have something preventing you from thinking that is the best route. So here's the situation. We're going to talk about this area here being you're in water, and over here, this is the shore. So all this is water. And here's you on this nice day in your boat. And you realize you're missing your calculus exam. You've got to get here as soon as possible. But to get there, you'd have to do a lot of rowing. This is the fastest, or this is the shortest route, but should you take that route if you're going to have to paddle and paddle and paddle? If you can't paddle as fast as you could possibly walk, if you paddle straight to shore, which is kind of a short distance, and then walked or ran, maybe that's a better idea because you can probably run faster than you're going to row. So the idea is, in terms of time, maybe it would be better to land here. So for sure do a little bit of rowing, minimize that whole leg, so a shorter leg here, and then run the rest of the way. Or maybe here, maybe land here, run the rest of the way. Maybe land here and run the rest of the way. So we're needing some spot along here that is going to give me the optimal situation. So I'm not going to pick a spot in the middle because then I might make some poor assumptions. Whether that spot is here or here, I totally don't know. I'm just going to pick that spot. So my plan is I am going to row to here. Okay, so this is on water. I'm going to row and then I'm going to run. So you need to be given some information. So let's say you're told you are 2 kilometers offshore. Let's say this entire distance from if you landed here to school, so here's school, is 6 kilometers. So the distance along here is 6 kilometers, and we need some information about how fast you can row. So here are your rates. So let's say you can row at 2 kilometers per hour. And let's say you can run at 5 kilometers per hour. Okay, so this is different from here. So where is this going to end up? Well, just like we did in distance problems, we're going to end up with a right triangle. So therefore I want to have knowledge of the 3 sides of this right triangle. Well, we're going to call this side distance as we did previously. Then I have this other scenario. So looking at this distance, the entire thing is 6. So think about it for a minute. Let's say this is 1. From here to here, if you landed kind of 1 kilometer versus your straight to shore distance, how much is this? Well, it would be 5. 6 minus this 1 would give you 5 for this distance. Or if this was 2 kilometers, 6 minus 2 would leave 4 for here. But we don't know what that optimal situation is. So this right now is unknown. But definitely, these 2 distances, one of them needs to be x, and the other needs to be 6 minus x. So 1 or a 1 would give me a 1 and a 5, or a 2 and a 2 here would give me a 2 and a 6. Together these add up for sure to 6. So I need a description for this and I need a description for this. Knowing we're going with the Pythagorean theorem here in a minute, Do I want this to be x and have to square an x, or do I want this to be 6 minus x and have to square a 6 minus x? I'd go for wanting that right here. So I would want my x there, and I would want my 6 minus x here. So I kind of have everything right now that I need in terms of identifying all these different lengths. So maybe right now, if you've been copying this, maybe it's a good time to just sit and watch what I'm doing. You can go back and copy the particular equations later. So understanding what's happening here is really important. So the idea is, what do I need to do? I need to follow this path, okay? So I need to be able to get time it takes for me to do this, plus time it takes for me to do that, and then I want to minimize that time. So looking at time, I need an equation for distance, and I need my velocity. So my rates are my velocities. So this v here is taken care of. I know those values. So how would I get the value for d? This squared plus this squared. So I know d squared would be x squared plus 2 squared. So d squared will be x squared plus 4. So d is square root x squared plus 4. So that's that distance, and that's that distance. So I have this and I have this for both routes. And velocities, I have both velocities for each route as well. So now I'm going to put together my formula for total time. So time is typically lowercase t. I'm going to use a capital T, just that that's now standing for my total time for this total trip, because there are 2 different legs to this trip. So my total time will come from the time it takes for me on water plus the time it takes for me on land. So if I do this and get expressions for time for each of these scenarios, then I can find the derivative. So capital T, what's my time on water? I need d over v for the water scenario. So the d is root x squared plus 4, and the velocity is 2. So over here, I have x squared plus 4 over my velocity of 2. That's time. The formula for time is d over v. And then I'm going to do the same over here, but with the relevant values for the second leg. So I'm adding the distance on land, which is 6 minus x, divided by the velocity on land, which is 5. So I'm ready to find the form, ready to differentiate, but this isn't looking as good as it could. I can change things a little bit. It would be to my benefit to look at this 2 down here as actually a front coefficient of 1/2, and to look at this as a front coefficient of 1/5. And so I'm just going to rewrite things that capital T, total time, is 1/2. I'm going to get rid of my radical sign by writing it like this. And then I'm going to have my 1/5 out front and my 6 minus x. This is where I want to be. I could multiply this out. That would be okay. I can't multiply the 1/2 through to here because of that exponent. So if I now decide to differentiate, I could call this t prime. Okay, so there's no squared here. I don't have to worry about implicit differentiation. What's the derivative of t? 1. But then it needs to be followed by t prime, because this is the dependent variable. Or I could say dt over dx, which is more informative. It's telling you that your total time changes as that decision of where you should land changes. So either one would be fine. I'm going to go just with t prime. So I keep my front coefficient of 1/2. I bring down that 1/2 and times them. I keep this expression the way it is. I take 1 away from here, which is negative 1/2, times it by the derivative of the inside. So that's the chain rule. And over here, keep my front coefficient. This is just a 1. I don't need the chain rule. What's the derivative of this? Negative 1. So I can fix this up definitely a little bit. One of these 2's here will cancel one of these 2's. So I'm going to have an x. So these are 2 separate entities. I'm going to have an x on the top here, a 2 in a denominator. This would go down below underneath a radical sign again. This would become negative. So moving things around to where they should be will give me t prime equals, let's see, I have an x on top, a 2, a root x squared plus 4 minus 1/5. That is the formula for slope. To minimize or maximize something, I want that to be 0. So you have different choices right now. You could find common denominators and then worry about making the top equal to 0. But because you have a binomial, why not just haul this 1/5 to the other side? You'll have 1/5 equals x over 2 root x squared plus 4. So I'd probably just apply cross multiplying. So now I'm going to have 5x equals 2 root x squared plus 4. You're going to square each side. So be careful on this side, right? You're squaring each of those values there. So here you'll have 25x squared. Over here you'll have squaring the 2 gives you a 4. Squaring this gives you just back your radicand, what you had there. And multiplying everything out, 25x squared, 4x squared plus 16, 21x squared equals 16. So we're going to have x squared is 16 over 21. Square root each side, remembering positive and negative. So square root of the top is a 4, square root of the bottom you would just keep as root 21. We typically don't worry about rationalizing in calculus. You could change this into a decimal as an approximation on your calculator. So we have, in terms of distance, we are going to take the positive value only, about 0.87 of a kilometer. But how are you going to answer the question? You can't say, I'm going to land 0.87 kilometers. From where? What is your point of reference? So you need to know what your x represented. So looking back at your formula, this is this 0.87. So how are you going to say that? Oh, if I went straight to shore and then from there 0.87 kilometers away I would land, that's not too practical. It probably would make more sense to put the 0.87 in here and figure out this distance. So if I did that, I would get 5.13 kilometers for this distance. So maybe a better way of phrasing your answer would be, you know what, I'm going to land 5.13 kilometers from school, and then I'm going to run the rest of the way. So remember, you need to finish off a word problem with a statement. So this would be better to say that you would land 5.13 kilometers away from school. Because careful, you just can't say I'm going to land 0.87 kilometers. That doesn't actually make sense. Okay, if somebody asks you, oh, how long would this whole thing take, by the way? Well, you would need your formula for time, right? Now you have the x value. So if you truly want to know the time it would take, go back to your time formula, or go back right here. And for that x, you could put in, 4 over root 21. And you could work that out. Then you would know, oh, what was the shortest time with all of those circumstances that I could get to my calculus exam on time. So if you want to try that, the answer would be about 2.1 hours. Oh my goodness, that's a lot. Or that would be about 2 hours and 7 minutes. Okay, so that was just one question, but knowing that setup of the 2 legs of a trip is really important. So you will have some homework. There is an optimization worksheet which takes you through optimizing distance, and then as well, here's your scenario of being on a little island, needing to get over here, or this one's starting here, getting to your little island, what's the best route, and then some of those distance problems that we did on the distance day. So there's this. Answers, I believe, I have up on the math website, so you can have a look if you're wondering about particular steps. And there as well is some work to do in your textbook. So have fun with that and spend the least time possible on this assignment. Bye-bye.